Welcome to this explainer. Okay, let's talk about a reality that most of us in the tech world know all too well. You've probably built a super powerful predictive model in Python using just a few lines of code, right? We all leverage those amazing libraries that just do the heavy lifting for us. But let's be real. For a lot of us, the actual underlying mathematics operating beneath those libraries, it still feels like this intimidating, impenetrable black box. Well, today, we're going to completely bridge that gap between your practical coding skills and those foundational math theories. Look, I completely understand that taking the hood off these algorithms is daunting. As Steven Strogatz brilliantly points out here, we often treat math like we're discussing spiders. And honestly, for a lot of coders, just looking at a dense page of Greek mathematical symbols triggers an instant fight or flight response. But today, we're going to disarm that fear entirely. Because once you see the big picture, you'll realize just how incredibly intuitive and deeply logical these concepts actually are. So here's our structural roadmap for the explainer. We'll kick things off with the math skills gap, transition into the 3 levels of mastery, build up the foundations and 4 pillars of machine learning, completely redefine what is a vector, and then wrap up by solving some actual real-world business problems. All right, let's jump right into section 1, the math skills gap. This is really the barrier between just using the software and truly understanding it. The real friction point today is that, sure, you can easily import a library and run a highly sophisticated algorithm. But to truly understand it, traditional courses expect you to already have a deep mastery of 3 massive, distinct areas. You gotta know programming, you need to navigate complex, large-scale computational frameworks, and you need advanced mathematics. It's just a massive wall of prerequisites, and it leaves incredibly enthusiastic practitioners stranded over on the software side, lacking the essential mathematical vocabulary they actually need to debug, optimize, and really grasp what's happening under the hood. Moving on to section 2, 3 levels of mastery. Think of this as mapping out your personal journey in machine learning. To figure out how to scale that wall, it really helps to view your machine learning journey through a musical progression. See, many of us start as an astute listener. You're just interpreting dashboard outputs and reading predictions. Then, as you master the software, you become an experienced artist, expertly stringing together APIs and libraries to do some seriously impressive stuff. But the ultimate goal? You want to become a fledgling composer. A composer understands the underlying math theory well enough to write custom loss functions, intelligently tweak parameters, or even invent entirely new model architectures from scratch. Which brings us to section 3, foundations and 4 pillars. The literal architecture of ML. Now, to actually become that composer, we need a visual map of the mathematics. Think of machine learning like a grand building. You literally can't put up the pillars of your algorithms without pouring the concrete foundation first. And that concrete base, it's made of deep foundational math like vector calculus, analytic geometry, matrix decomposition, and probability. These raw elements interlock to give you a rock-solid base, which then supports the 4 main architectural pillars of all machine learning applications. Let's look at those first 2 pillars, which deal exclusively with predicting outcomes from known data. On one side, you have those flowing blue and red trend lines mapping out continuous, real-valued predictions. That's regression in action, constantly hunting for that perfect line of best fit. Contrast that flowing line with the distinct, clustered boundaries, grouping data points into strict categories on the other side. That's classification. It's drawing absolute borders to decide, hey, is this email spam or not spam? Or is this image a cat or a dog? The final 2 pillars deal entirely with unlabeled data, where the algorithm is basically flying solo and has to find structure on its own. For this, we use Dimensionality Reduction. This takes massive, chaotic data clouds and neatly compresses them into tight, readable 2D maps without losing the core essence of the information. Meanwhile, density estimation acts exactly like a topographical map. It reveals the hidden structural probabilities and peak densities lurking right beneath the surface of the dataset itself. Okay, let's move into section 4. What is a vector? It's time to redefine the familiar. Let's drill right down into that concrete foundation we talked about, specifically linear algebra. As computer scientists, we're totally trained to view a vector as just a one-dimensional array of numbers in a codebase. But mathematically, we need to zoom out and completely shift that paradigm. A vector is defined entirely by its behavior. If you can add an object to another object of the exact same kind and you can scale it up or down, boom, it's a vector. That is the golden rule. We all remember the classic geometric vector from high school physics, right? The standard directed arrow. It perfectly obeys our golden rule. If you take one arrow and stack another directly on its tip, or stretch it out to double its magnitude, the resulting shape is still just an arrow. It fundamentally follows those rules of addition and scaling. But prepare for an absolute eureka moment. Highly abstract objects, like polynomials, those sweeping mathematical curves, they can be added together or scaled up too. Even complex digital audio signals can be overlaid and their volume amplified. Because they strictly obey those two simple rules, they are completely valid vectors, meaning we can treat an audio file or a financial curve mathematically the exact same way we treat a simple physics arrow. How cool is that? In this realization, it's the secret translation layer that makes literally all of machine learning possible. By translating messy, chaotic, real-world concepts like user behaviors, voice recordings, or high-res images into a mathematical n-dimensional space, we give our algorithms the actual power to process reality. We map the physical world into numerical vectors so our computational models can optimize, learn, and accurately predict. Let's make this totally concrete in Section 5, Solving Real-World Problems, Grounding the Math. We never want to leave this hanging in the abstract, so let's ground this theory in a tangible business scenario. Imagine you oversee a sprawling manufacturing plant. You're dealing with strict raw material limits, super complex product lines, and rigid resource constraints. By representing this entire ecosystem as a comprehensive matrix of linear equations, you aren't just guessing how many units to produce. You are quite literally asking the underlying geometry of those vectors to calculate the absolute optimal production plan for your business. When framed this way, the math becomes your ultimate objective source of truth. It'll definitively calculate if your resources can balance in perfect harmony, giving you a solvable equation. Or, on the flip side, it will immediately flag if your constraints fundamentally contradict one another. This kind of mathematical foresight can literally save you from a massive operational breakdown long before a single machine on the factory floor is ever turned on. So, you know that intimidating wall of math prerequisites we looked at earlier? Actually, scratch that. It's not a wall at all. It's just a staircase of deeply logical foundational tools just waiting to be used. The only question left is, how far are you going to take your journey? Are you going to remain on the sidelines as an astute listener relying on off-the-shelf code? Or are you ready to use these mathematical principles to compose the future of machine learning?